This is the last video of the exam review. I wanted to add this in because I did edit some of the questions, and in the original video set I did not do problem number 25, so I'll be skipping around. Just follow along in your packet. This is problem number 5. It tells us to use the graph of f. Now the first thing I want you to observe is that f is the original function. To determine each of the following. Letter A. Where is f, the original function, not continuous? Now remember, for continuity, we're looking for either a break, a gap, or a hole. That's where a function is not continuous. And it's very easy to see that in this problem, there's a discontinuity at x equal to 1 because there is a hole in the graph. In other words, at that value of x in the domain, there is no output, there is no y value. Now, I'm going to skip over A and I'm going to go to letter C because we're going to have to write a sentence explaining why, using good mathematics, why the function is not continuous. And there are 3 reasons why a function may not be continuous. The first reason the function might not be continuous is f of C is not defined. What does that mean? That means when x is equal to c, there is no y value. So the function does not generate a y value for that particular x value, and that's what leads to having a hole in the graph. A second reason why a function might not be continuous is because the limit as x approaches c, c is a particular value of x, of that function does not exist. What does that mean? There is no limit at x equal to c. Now, there are a variety of reasons why the limit might not exist, but that's not what this question is about. This question is about why is a function not continuous. The third reason that a function might not be continuous is a combination of these two, 1 and 2. The reason there would be is that the limit as x approaches c, in other words, there is a limit of the function, but that limit is not equal to the y value. And that would often lead, not necessarily always, but that would often lead to a jump discontinuity. Actually, it would not lead to a jump discontinuity. It would be something like this. So we have x equal to c. I'm going to call that c right there. There is a limit, open circle, and there is a y value, but they don't equal to each other, so the function is not continuous. There is a y value, there is a limit, but they don't equal each other, so the function is not continuous. All right, so let's go back up to letter A. I would say there, f is not continuous at x equal to -1 because f of -1 is not defined. In other words, there's no y value there. Letter B, where is f not differentiable? So I'm going to clear the board. For differentiability, what we're looking for are sharp turns or cusps. Now again, you cannot use that as a reason why the function is not differentiable. This is just simply what we're looking for. So on this graph, there is a sharp turn at x equal to 0. So the function is not differentiable at x equal to 0. There is a sharp turn at x equal to 2. And there is a sharp turn at x equal to 3. These numbers are a little bit off from where they should be. So there are 3 places where the function is not differentiable. Oh, I'm sorry. And also there's a 4th place where the function is not differentiable. The function is not differentiable at x equal to -1 because the function is not continuous at x equal to -1. So one thing you need to remember about differentiability, if the function is not continuous, then it can't be differentiable at that value. Remember, differentiability, let's write that down, differentiability implies continuity, meaning that if a function is continuous at a particular value of x, I said that backwards. If a function is differentiable at a particular value of x, then it is also continuous at that value of x. But it doesn't work the other way around. Continuity does not guarantee differentiability. All right, so let's write up a couple of these. I'm going to start with x equal to -1. So I'm going to put my answer down here. F is not differentiable at x equal to -1 because f is not continuous at x equal to -1. Now, let's pick one of the other ones because it's going to be the same reason for either of the three. I'll do x equal to 2, so I'm going to justify why the function is not continuous at x equal to 2. I'm going to say, let me get myself some more paper here. F is not differentiable at x equal to 2 because, now what's happening here, if you recall, and you may have to go back and study this, I think I gave you some pages in your packet to look at when we reviewed this before. At x equal to 2 right here, the derivative on the left, notice that all of the slopes here were on a linear segment. The slopes on the left-hand side are not agreeing with the slopes on the right-hand side. There's not that slow, gentle guiding that we talked about a couple of months ago. So I would say because the limit as x approaches 2 from the right-hand side of f of x minus f of 2 over x minus 2. Now, that's your slope formula. Basically, what you're saying is that the left-hand slope does not equal to the right-hand slope. So x approaches 2 from the right-hand side of change in y over change in x. You you should review that in your packet to make sure you understand how to write up that differentiability. All right, the next problem that we're going to take a look at that I changed, let me see if I can figure out which one it is problem number 17. I think I added letter F to that question. Determine the absolute maximum and absolute minimum on -3, 1. Use complete sentences to justify your answer. So in this problem, we're looking for the absolute maximum and the absolute minimum. So of course, this is the extreme value theorem. The extreme value theorem says that we can consider as candidates the critical numbers and the endpoints. And of course, critical numbers are where the first derivative is either 0 or undefined. Now what we have here is a graph of the first derivative. And the first derivative is 0 at x equal to -3. So we have a critical number at x equal to -3. And we have a critical number, well, what interval we're looking at, from -3 to 1. So let's block off the graph. So even though -3 is a critical number, so from -3 to 1. All right. So -3 is a critical number for the graph, and x equal to 1 is also a critical number for the graph. However, they are the endpoints. Between x equal to -3 and x equal to 1, there are no critical numbers. Now, you may be looking and thinking, well, isn't there a critical number at x equal to -1? No, this is the graph of the first derivative, and we're trying to get absolute maximums of the original function. All right, so we have no critical numbers in this case, but we do have endpoints, and we're going to compare our endpoints. Notice that the graph of the first derivative is positive over the entire interval. Since the graph of the first derivative is positive, then the original function is increasing over the interval. All right, so again, the graph of the first derivative is positive, so the original function is increasing over the interval. That means then that f of 1 has to be the absolute maximum. So let me write that up for you. Determine the absolute maximum and the absolute minimum. F of 1 is the absolute maximum comma, and f of negative 3 is the absolute minimum because f prime of x is greater than 0 on negative 3 to 1, comma, therefore f is increasing over the entire interval. Okay, let's see what the next item is. The next item that I added some parts to number 19. The average rate of flow during the first 8 seconds, I think, is in the original video. I'll go ahead and say it. If we're going to find the average rate of change, we're just doing change in y over change in x, so we're going to do a simple slope. Letter B, we're estimating the instantaneous flow at x equal to 4, so we're going to go one above and one below, and we're going to do an average. Letter C, in a complete sentence, interpret the meaning of r prime of 6. All right, let's go back to the problem. Chemicals from a storage tank are leaking into a pond. The flow is measured at intervals and is recorded in the table below, where T is measured in hours and R of T in gallons. R of T is differentiable over its domain. All right, so R of T is a function that is measured in gallons, and we want to interpret r prime of 6. Well, some things that I noticed. First of all, this whatever's happening here is occurring at 6. Does it tell me the time? Hours. So T is in hours, and R of T is in gallons. So whatever's happening is happening at 6 hours. I noticed that the sign of the derivative is negative, so something is decreasing. So we want to ask ourselves, what was this problem measuring? It was measuring chemicals that were leaking. So the chemicals are decreasing, and they are decreasing at a rate of 2.5 gallons per hour. So my complete sentence would be at 6 hours, the amount of chemicals leaking into a pond is decreasing. That takes care of the negative at a rate of 2.5 gallons per hour. Now notice here I did not say decreasing at a rate of negative 2.5. The word decreasing takes care of the negative. Make sure that you don't state both because it will be counted wrong. Letter D, using complete sentence, explain why on the interval from 6 to 12 there must be a value C where f of C is equal to 10. Okay, this is a theorem question. We've been given a closed interval. We know that the function is continuous because it's differentiable. And it's also stated that it's differentiable, so it meets criteria for many of our theorems, the mean value theorem, Rolle's theorem, intermediate value theorem. But notice what they're saying here is that there is a y value where f of c is equal to 10, and f is referring to, I should say r of c is equal to 10, but it's referring to the data in the table. So we know from the table that when x is equal to 6, y is equal to 30, and when x is equal to 12, y is equal to 8. And again, I got those values from 6:30, 12:8. Use a complete sentence to explain why there must be a value of x where the y value is 10. Well, I mean, you can use common sense. 6:30, we'll call this 6, and 30 is way up here, and 12:8 is here. If the function's continuous, whether it goes up and down, whatever it does, it's going to have to pass through 10 to go from 30 to 8. This is the intermediate value theorem, which is a promise, y-value promise. So let's write my complete sentence. There must be a value c when f of c is equal to 10 because f of 6 is 30, f of 12 is 8, the function is continuous on, 6 to 12, so there must be a c when f of c equals 10 by the intermediate value theorem. Sorry, that's a little bit sloppy and some of it's redundant. Probably I would revise that a little bit, but you get the idea. I'd rather overstate than understate. Letter E, must there be a time t? Let me clear the board here. Must there be a time t? I'm trying to clear the board here. Must there be a time t from 0 to 16, so from 0 to 16, where r prime of t is equal to 0. All right, so now we're asking about a derivative. And since we're talking about a derivative, we're probably not talking about the intermediate value theorem. More likely, it's either going to be Rolle's or mean value. Now remember that Rolle's is a special case of the mean value theorem. And they're talking about the first derivative being equal to 0, so I'm thinking about Rolle's, but we can also use the mean value theorem, either one. All right, let's find out. We know that we have all the conditions are met. We have a closed interval, our function's continuous, and it's differentiable on the open interval. So the endpoints, if we look at 0, we have a y value of 40, and when we look at 16, we have a y value of 3. So notice that f of 0 is not equal to f of 16. So by Rolle's, we're not meeting all the criteria of Rolle's theorem, so we can't guarantee that the derivative will be 0 at some point. So that's justifying by Rolle's theorem. So I would say, no, there is no guarantee that r prime of t equals 0 because f of 0 is not equal to f of 16. Now notice I didn't state the other criteria that were met. All I have to do is find one that is not met. Now we could also use the mean value theorem. If we tried to use the mean value theorem, what we'd be trying to show is that the average rate of change is not equal to the instant rate of change. And they're telling us here that the instant rate of change is 0. Well, very easily, if I wanted to use the mean value theorem, then I would do change in y, so 3 minus 40 over 16 minus 0, which is going to give me negative 37 over 16, which is not equal to 0. So I could say by the mean value theorem, the average rate of change is not equal to the instant rate of change. So either one of those would be okay to justify. And let's see what our next problem is. Finally, problem number 25, which is actually a very important problem for the exam, and for whatever reason I didn't do it in the original exam review series, so let's take a look at this one. Complete the following without the use of a calculator. We've been given a position function called s of t. We want an expression for the velocity function. Remember that velocity is the first derivative of position. So I'm going to use the power rule and get 3t squared minus 12t plus 9. Let me check that. 3t squared minus 12t plus 9, that is my velocity function. When is the particle at rest? A particle is at rest when the velocity is equal to 0. moving to the left when velocity is less than 0, and moving to the right when the velocity is greater than 0. So I'm going to set the velocity function equal to 0. Now I'm going to divide both sides by 3 to make my number smaller, so that'll give me t squared minus 4t plus 3. I'm going to factor. Please do not try to subtract 3 from both sides. I get a 3 and a 1 and a minus and a minus. T is equal to 3. T is equal to 1. I'm going to create a velocity number line. So this is v of t. I'm going to put my critical numbers of 1 and 3. I'm going to choose a value less than 1, like 0, and sub it into the velocity function. When I substitute 0 into the velocity function, I get a negative times a negative, which is a positive. So the particle is moving to the right when the velocity is positive. I'm going to choose a number between 1 and 3, like 2. When I substitute 2 into velocity and I find v of 2, that'll give me a negative times a positive, which is a negative, so the particle is traveling to the left. And then when I choose a number larger than 3, I will output a positive. The particle is traveling to the right. The particle is stationary or at rest at t equal to 3 and t equal to 1. So at rest. I'm not going to write these answers up or justify them. You've seen the answers, and you justify them by stating whether the velocity is positive, negative, or 0. Letter C asks for the speed of the, edit, undo. Eraser is what I wanted here. Letter C asks for the speed of the particle. Remember, let's change colors here. For letter C, that speed is the absolute value of velocity. So speed at t equal to 2 would be the absolute value of v of 2, which is v of 2 is negative 1 times 1, which is negative 1. The absolute value of negative 1 is positive 1. So the speed is 1. They didn't give me any units here, so we'll just say that the speed is 1. Hopefully I substituted that correctly. 2 minus 3 is negative 1. Yeah, that's right. Letter D, I need expressions for the acceleration of the particle. Acceleration is the first derivative of velocity. So a of t, again I'm using the power rule, will give me 6t minus 12. And then lastly, letter E. Careful here, what is the minimum? This is the extreme value theorem. But the minimum of what? The minimum velocity from 0 to 3. The minimum velocity. So, to apply the extreme value theorem on velocity, I need the critical numbers and the endpoints. But be careful, I need those for the velocity function. Well, how do you get those? You go to the first derivative of velocity, which is acceleration. So to get velocity's critical numbers, I'm going to set velocity's derivative, which is acceleration, equal to 0. Solving that gives me t equal to 2. T equal to 2 is a critical number for velocity. I got that out of velocity's first derivative. The extreme value theorem says I need to compare the endpoints and the critical numbers. So the endpoints are 0 and 3, and the critical number is 2. Remember, we're trying to find the minimum velocity, so plug these values into velocity. When I plug 0 into velocity, I get 9. When I plug 2 into velocity, I get negative 1. Remember, we did that earlier for part C when we did the speed. And when I substitute 3, I get 0. So the minimum velocity of the particle occurs at 2, and the minimum velocity is negative 1. Pay attention to letter E very, very carefully, and come in and ask me questions if you have them.